In section 4.8, what we're going to be doing is using Newton's method to get the roots of a particular function. Now, we've dealt with quadratic functions, and in which case when we want the roots we use the quadratic formula. Cubics are a little bit harder, and then when I start getting into higher degree polynomials, it becomes increasingly difficult to find the roots or where it crosses that x-axis exactly. Newton's method is a convenient way to find these roots numerically. And what they have me do is choose an x naught as close to the root as possible. So you'll notice that they had us choose as our first x naught a -3, because that's pretty close. And I could have chosen -2 as well, but they had us choose x naught equal -3. So that's where we're going to begin. And this is 3 separate problems here for 3 separate roots. So we'll get each of those roots. And these are going to be our iteration numbers. They'll say, you know, for the first one, for the second one, for the third one. That's what this 0, 1, 2, 3 is about. And I will need the derivative. So xn plus 1 is going to equal x to the n minus my f of x, which is x cubed, minus 5x plus 1 all over 3x squared minus 5. Now for our very first case, I'm going to need, so let's do it for this x naught is 3. So first off, x naught equals -3. Then x1, plugging in the 0 plus 1 here, would be equal to x naught, which is -3. I'm just going to write that in instead of writing down the equation again. Would be the -3 minus, and then I would plug in these all here, but I have my little n's in here for that particular. So what I would then do is replace in here those values, that -3, because it would be the x naught. So I would need to do -3 quantity cubed minus 5 times -3 plus 1. And this involves a lot of computation. So, you know, you get tired of doing all this computation, and it does actually get you an answer. Then you'll use this answer, and then you'll plug it in for your next ones. That's what I'm going to do. I'm going to do this with my calculator first, and then with Excel. So let me crunch these numbers. Now, if you want to make it easier to plug in on your calculator, you can simplify this a little bit, getting a common denominator, and right here getting the common denominator of 3x squared minus 5, and then combining the top. If you do that, you'll get this 2x to the n quantity cubed minus 1 over 3x squared minus 5. You don't have to do that, but if you want to, you can see it would be easier to plug it in. It really doesn't matter one way or the other if you want to use your algebra to make that a little simpler. And then the next thing, you would do x2, and then you would plug in this -2.5 everywhere we had a -3 in this case. So I'll write all that in. And then you would need to chunk that into your calculator, and then you would get -2.34545, blah blah blah. Alright, and I would do this a bunch of times until I came up with a consistent number right here. Once I came up with a consistent number, then I would know that that's probably about what the root is. I would do that for this first one, then for the second one, then for the third one. This is really quick and easy in Excel, so we're going to look at how to do this in Excel. Alright, so here we are at Excel. You'll notice I am keyed in on this cell. I keyed in the formula. This cell happens to be B3, so you'll say I said 2 because I want 2x to the n quantity cubed minus 1 over 3x to the n quantity squared minus 5. So that's what this says. This says whatever number is in B3, raise it to the third, and then the next thing I did was I then changed these B3s for my next iteration, because I just wanted to do this again, and I'll walk through this with you, but I changed it to look at the cell C3. So this one I had it look at C3, that way it used the negative 2.5 in its calculation. This one looked at C4, this one looked at C5, and so on. Alright, so let's look at our Excel and see how we're going to do this. Alright, over here I just wrote down the iteration number just so that we would know what it was. We don't really need that. Here I just wrote in what it was that I was starting with. I started with x naught equals negative 3. Don't really need that in there either. So let's just plug in here our negative 3 because that's the number I wanted. In this cell I wrote in the equation, and that equation is, in order to tell Excel you want an equation, you do equal to, and I'm going to do the open parenthesis, and I want it to take this negative 3. I want 2 times that negative 3, so I'll say 2 times whatever is in B3, and then I'm going to raise that to the third power minus 1, and then I will close that parenthesis, and then divided by open parenthesis. I'm going to want the 3 times that B3 raised to the second minus 5, close parenthesis, and then I'll tell it enter, and it gave me the negative 2.5. Now I kind of want more digits here, so what I did was I went into I just right clicked actually, and I said format cells, and then I wanted a number, and I want a bunch of decimal places, so I say I want a bunch of decimal places, and then I'll just say OK, and then it kind of extends that cell for me. But you can extend that cell by asking it to format and then just do column width, and you can tell it to do it on its own. Alright, so the next time I want it to use negative 2.5, so what I'm going to do is I'm going to Control C, I'm going to copy that cell, and then I'm going to paste it right here. And I need to adjust it because it's using whatever is in this. You'll notice it's using whatever is in B4, and I have nothing in B4. Notice the formula said that. So I don't want B4. I want it to use H3. H3. And right here I want it to also use H3, and then I'm going to say enter, and you'll notice that I get the same things over here. And oh, I forgot, actually I wasn't really using B3 again, I was using in this case G3, so I guess I should make that a G3 just to make it correct, and then go over here and make that a G3. Okay, still get the same answer, but alright, so now what's nice about Excel is this is the equation that I want. I just want it to use the one previous. So I'm going to say Control C, that cell, and then I'm just going to tell it, oops, I know, okay, oops, undo, okay, so I'm just going to tell it I want it to drag this down, if I can actually grab it this time, and just say enter, and you'll notice I get the same thing that's over there. Nice, and it looks like right at about the 5th iteration it doesn't change anymore, so I'm going to, and really it's so darn close after the 3rd iteration, I'm going to say that 0 is right there at negative 2.33. That's pretty handy. Now notice, since I want to do it for x equal to 1, I can just say, well, I don't want to do it just for there. So you could, on a test, if you were having to show work, which you have to, you can show me your formulas that you've plugged in there, and then you can just give me a few snips and it will show me exactly what you've got in here. Now let's say I want to start with the root at 1. I just plug in enter, and now I get exactly the same thing that I have down here, and that gives me, I don't have to do any plugging in. The hard part is the setup on the first two. My root is probably at positive 0.2, and we'll look at that graph here in just a minute. And then the other one I want to do, I think I'm supposed to plug in at 4, and I just hit a 4, And notice it changes all the numbers for me, and that is really easy to use Excel with Newton's method. So let's come back over here and notice that I still had a pile of work left to do. I was only on the second iteration by hand, but with Excel I have them all done. So let me just slap those down on there. Note how in this x not equal 4 one, I have the cell highlighted so that the reader can see my equation that's in there. When I ask you to show your work, if you use Excel, please highlight the cell so that I can see that your equation is in there. Otherwise I just see numbers, and I'd like to see what your equation is that you have plugged in there. And this is for this first root is at negative 2.33. This next root is at 0.202. This one is 0.202, and this one happens to be at 2.13. And I've used Newton's method to get those three roots and Excel. Alright, this is just a little blurb about when do you stop and how close it is that you want it. And notice that, if your values on like the fourth and the fifth iteration agree to 7 digits, general rule of thumb is if you have 7 digits and you have 2 successive approximations that are the same, you can probably stop. You can use Newton's method for finding intersection points. Newton's method doesn't have 2 functions, but if this is just the place where these functions intersect, so I know that their subtraction would be 0. So just let f of x equal to, say, cosine x minus x, and then you would find the derivative there. So this can be minus sine x and then minus 1. Newton's method tells me I can use this, x to the n, and then that would be minus, and then the f of x, which is cosine x minus x over negative sine x minus 1, and we can roll from there. We'll need a graph to kind of help so we can get a good guess for our very first root that we would like to find, and however many that there are. Alright, and some of you probably know that you can use your calculator to get a numerical estimate of a 0, but that's not using Newton's method. So if you're asked to use Newton's method in order to find the 0, you will need to prove that you use Newton's method. This is called using the calculator to get the 0, but if I was taking a test, I would probably use the calculator to reinforce that my Newton's method was correct. I would probably, this is the equation that I need to use for Newton's method. I'm going to go put it in Excel, and let me put my little xn's here, and I am graphing. Notice that I graphed in radians. I'm going to choose, say, it's around 1 or a half. You choose whichever one you want to put in. Let's choose to put in, say, a 1. We're going to let x naught equal 1, and we're going to see if we can get our root from there. I'm going to go over to my Excel chart and plug in that formula and go from there. Alright, I'm not going to simplify this. I am just going to plug in my 1, and I'm going to run it from there. Alright, here goes. Equals to, open parenthesis, I want what's in cell B3 minus, let's do open parenthesis, cosine of B3 minus B3, close parenthesis for the numerator, all over open parenthesis, negative sine of B3, close parenthesis, minus 1, close parenthesis, the denominator, close parenthesis, the whole thing. Let's hit enter. Alright. So it gives me this number here. Now that's the number I want to plug into this formula here. So I will just take and Control C this, Control V here, and change all of those B4s because they're plugging in a 0 at this point. I want them to all be C3s. So every B4 I'm going to change to a C3. So I got to get in there and just do C3, 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 enter, and then I'm just going to drag this sucker down if I can grab it this time. Oops, take those and drag them on down into here. And there we have it. Looks like it doesn't change after the third iteration. I would say that this root is at 0.739. So this root and you'll notice I could have done this with the calculator. Let's look at what the calculator got. Notice these two totally match up. That's very convenient. This is using Newton's method because I had to use both the function and the derivative. Using the calculator once again is not using Newton's method, but it does verify that I got it right, or that I think I got it right anyway. This next example wants us to find the local extrema. So that means I will need to find the critical points. So I'll find the first derivative, and then I have to figure out where the first derivative equals 0, which means I'll be finding the roots, which means then I will have to use Newton's method. So here I see the product rule. The product rule says let's take the derivative of the first, that's e to the negative sine x, using the chain rule. Leave the second guy alone, plus e to the minus x. Take the derivative of the second guy. That involves the chain rule. That would be cosine 2x. Chain rule says take the derivative of what's inside. That would be a 2 out front. And now I have to figure out where this dumb thing equals 0. I try to take out some things that are common. I see that I can take out this, which would make it a little simpler. So I now have negative sine 2x plus 2 cosine 2x. Okay, I can figure out where this guy equals 0, where e to the negative x equals 0. Let's see. Oh wait, that wouldn't, would it? Because that is a function that looks like this, and that never equals 0. So I need to figure out where this guy then equals 0. What I have graphed for you here is just this negative sine of 2x, and notice that they wanted this for the interval 0 to pi, so they just want it in between 0 and 3.14. So they want the roots in this viewing rectangle. I see that I have two of them. I have one right here, and then I have one right here. I will let my first x not equal 1 and find this 0, and then I will let my next x not equal, let's say, 2 and find that 0. And of course I'm going to use Excel, so I'll plop that up here. Okay, just so that you'll note, I started with x equal to 1, and here's my equation for my B3 where I plugged in this formula using this one. This next one uses the C3, so it uses the value previous, plugs it all in, and I end up with that root being at 0.5535, which is a critical point. That means extrema can occur there. And I would like to do the other one, so let's see if I can do it kind of quickly. I'll just take, whoops, not going to be that quick. Try that again. I'm going to take and I'm just going to copy from here. And I'm just going to say Control C, tink, Control V. Oh, I know. Let's make this one a little bit wider. Format, column width. We'll just make it 15 wide so it'll actually read in there. And I said I was going to choose one of them to be at 1 and one of them to be at 2. And Let's see if my formulas are right. This one uses F3, that was what I wanted. And this one uses G3, that was what I wanted. That one uses the prior one, G6. Okay. Looks like I have two roots, one at 0.55357436 and the other one at 2.12. Fun. And those would be my critical points. And I can choose those to be my maximums and minimums. I probably should look at my graph. Alright, here's the graph of the entire function, and it says that I can see that I have a local max, and that one is going to occur at that, that is going to occur at this 0.5535, and then my local min is occurring at the 2.12 right there. Nice. Now, as you well know, this probably doesn't work in every single case. The very last example that they do in this section shows a case where it doesn't quite work. Not go through that. What happens is they don't go to a single value. It kind of bumps around. And so if it's bumping around and it's going, say, positive to negative, or it's just jumping all around and not going to a single value, then you conclude that Newton's method probably isn't going to work for that one.